everyone. Today we're going to focus on Lewis structures, and I know that you probably have already done Lewis structures last year, but I just want to go over the rules in which we draw Lewis structures, as well as do some examples of these Lewis structures, because on Thursday in class, you're going to model several different examples of Lewis structures for me. Okay, so for the most part, also in this chapter, we're going to focus on, or at least in this video, we're going to focus on drawing Lewis structures for molecular compounds. A lot of times, it's just much easier to see a molecular compound in terms of drawing its Lewis structure, so that's what we're going to focus on today. We can also draw Lewis structures for ionic compounds, but I don't know that I have any of them in here, but it's okay, we'll still do some practice so we can see what that looks like. Okay, so ultimately a Lewis structure is drawn because it shows a representation of how all of the electrons are either bonded or how they are not bonded. So it shows paired and unpaired electrons, and those are really important in determining how a specific atom or how a molecule could bond or change in a chemical reaction. So for the most part, we predict what Lewis structures will look like based on our valence electrons. So if I'm just looking at the hydrogen molecule, I have hydrogen has one valence electron. So two hydrogens come together with those one each valence electrons. They each are bringing in that one electron. So ultimately they're going to share these electrons. Now what actually happens if I'm thinking about it in terms of this 3D realm, or if I'm thinking about it in terms of that electron cloud. So I have this electron cloud, this has its own electron cloud. Those clouds are going to come together and overlap. So I'm actually, where these two electrons are, I have an overlap of these two s orbitals, okay? So this is an overlap, and I want you to think about it that way, because when we talk about a single bond versus a double bond versus a triple bond, every single, each of these bonds is going to differ a little bit in how it behaves just because of the overlap between these atomic orbitals, okay? Now chlorine is the exact same thing. Chlorine is going to have 7 valence electrons each, so because of that, these two can share. I see that there's this atomic overlap here, and that's what gives me my 2 shared electrons, or the one single bond. So if I want to represent drawing hydrogen in a different way, instead of drawing it with the Lewis dots, I could draw it like this. I could draw the Lewis structure to where instead of representing 2 electrons as dots, we can represent the 2 electrons as a single bond. So one single bond is representing 2 electrons. If I'm talking about a double bond, it's going to have 2 electron pairs. And if I talk about a triple bond, then that has 3 electron pairs. So if I can write hydrogen this way, chlorine also shares 2 electrons, so I can also draw the chlorine with the single bond. Okay, but we know that not all Lewis structures have single bonds. And the reason that they don't all have single bonds is because many atoms will attain a complete octet by sharing more than just one pair of electrons. So there are a few examples that I wanted to look at first of all, and that's carbon dioxide, and then also the diatomic nitrogen molecule. So let's actually, instead of looking at it here, I think it may help to just draw them out. So carbon, we know, that was a terrible C. Carbon, we know, has 4 valence electrons. So I'm just going to draw carbon like that. And then I know that oxygen has 6. And I'm actually going to draw it like, actually going to draw it like this. But it has 6 here, but just stay with me for me drawing it that way. And then oxygen over here, if we're talking about carbon dioxide, also has 6 over here. Okay, so my goal is to try to get this so that every single one of these atoms has a fulfilled octet. So I have one space here, it could share an electron, and then I could share an electron here as well. Well, carbon has an electron here, so maybe I could make a bond here. Carbon also has an extra electron that could fulfill the octet for the oxygen here. So I'm actually making a double bond on this side. And if I do that here, this side is the exact same way. So ultimately, these can share, and these can share. So really what I've done is now oxygen is double bonded on each side to this carbon. And it has still these two unpaired sets of electrons that remain. But let's check, because Lewis structures are all about fulfilling this octet rule. And to do that, I need to make sure I think about, are each of these atoms then in this molecule fulfilling that octet? So carbon, if each of these single bonds represents 2 electrons, and I have 4 of them around, carbon has 8 electrons around it. Oxygen has 4 unpaired, and then 4 that are bonded, it has 8, and then this one also has 8. So I can see that it doesn't need to just be a single bond. I can fulfill octets also by having a double bond or a single bond. There's a different way to do it than this. We're just doing something really quick because we need to make sure that we're following the rules of drawing Lewis structures, okay? The nitrogen molecule is the exact same way. Nitrogen has 5 valence electrons. So ultimately what it's going to do, it's going to share one here, these are going to share, and then those outermost ones are going to share. And that's going to leave me with a triple bond, and then one lone pair of electrons on each of the nitrogens, okay? Okay, so I can see that we just did the carbon dioxide. The Lewis structure should look like this. It fulfills the octet. My nitrogen molecule will look like this. It also fulfills the octet. But let's talk about the length of these bonds, and then also how length indicates also the strength of a bond. So it says right here, the carbon-oxygen bond length in carbon monoxide is 1.13 angstrom.